most of the students. So I gather either it's because a lot of the students don't accept the invitation I sent to them, or they use a different email address from the one they sent me. So that makes it very difficult, because once I start presenting or showing my slides, it's always very difficult to continue going back to admit other students. That also explains why I have decided to give more time for others to join. I see we are about 40. That is half the class, so at least that's quorum enough for us to begin. And so I will just begin. Hopefully, I will not get a lot of these interruptions of admission. Let me see if it's possible to provide these rights to somebody else so that we continue uninterrupted. All right, so I will share my screen with you so that we begin our session in a minute. Please just notify me. Any one of you can just let me know if you can hear me properly and you can see my screen. I'd really appreciate that.
Yes, we can see the screen, sir.
Thank you very much. All right, now, it's, as you're well aware, we are going to be discussing 511, which is control engineering. This is a 45-hour course. I intend, based on your program and the timetable that I saw, that we try as much as possible to race through this content until the first week of December, when you're most likely going to begin your exams. I'm not too sure, but we'll see. Now, I also want to apologize for that the last 2 weeks we have not done anything, and that has been because we had a crash program in terms of the supplementary exams. So we had to invigilate the supplementary exams and mark them and submit them into the system. And so that took quite some time. But at least now I'm sure we're going to be able to attend all the other subsequent classes just to catch up. Now, the other thing is I want to just start by introducing this course and that which is expected of you. But as I do that, I request all of you to, I hope you have your notebooks and you have your pens, because you need to make notes. A lot of the things that I'm going to say, I do not have notes for. So it is important that as we present this lecture, that you also take notes as much as possible. I will provide some structured notes later on, but I currently do not have what I'm going to share with you written down. So to save yourself, please make some notes. That also keeps you active within the class, because it's a 2-hour class. Now, in control engineering, we are going to discuss what our main objective, the reason why we want, let me just call it the purpose of this course. I think you should be able, through your class reps, to also obtain the course outline from the admin, that is from the secretaries. So I will not have to go through the entire thing because of time. I'll just have to brush through some of the key areas. So here we need to develop control system design techniques. Control system design techniques. And not just to develop these design techniques, we also need to introduce, so I think I'll just put another one here, which is like to introduce, because this is important, very, very important, analytical techniques. We need to introduce analytical techniques. Okay. And these analytical techniques are mostly used in non-linear systems. I am sure by now, at least you can define what a non-linear system is from a linear system. But my key concern is that we try as much as possible to see how we can develop our own design techniques using certain very important analytical tools that you'll be introduced to. The two main tools that we are going to use are, number one, we are going to use the root locus method. So the root locus method is going to form a key subject of study throughout the entire semester. But over and above that, we are also going to use the state space method, which is also a very important technique, state space, the state space method. Now, ladies and gentlemen, these two methods are very critical in helping us analyze and design control systems. I know we have been exposed to different other methods before, either in as we do our maths, or at least when we introduce control systems at certain levels. But at this level, in your final year, the two key methods are the root locus method and the state space method. Now, I know that systems can be analyzed using several methods. You've used Laplace transforms, we've used Fourier transforms. There are so many methods that help us model systems. But in the analysis and design of control systems, we are going to focus on root locus method and the state space method. But again, I hope we'll have time to look at nonlinear systems and see how we can also model nonlinear systems or analyze the performance of nonlinear systems. So the course outline basically is going to be the root locus method and the state space methods. If we are able to do that, we'll be home and dry. This lecture, as I have told you, is going to be a mixture, and it is on your timetable, that it's going to be a mixture of online and physical classes, but I'll only restrict myself to online classes for the next 2 or so weeks. Then we resume the physical classes. Now, again, because you as a student are expected to do 70% of the course on your own, while I guide you with 30%, I will try as much as possible to provide more, just to make sure that you as a student are able to gather as much information as possible on these techniques, because these techniques will be used not only in class, but also in the industry. So it is important that you gather as much information as you can on these techniques. The reading materials that I can't indicate here, you know, this is control system. So I'm sure even in your 4th year, actually, let me mention that I think you did, I don't know, you were taught control systems 412. This is a prerequisite. This is very important. If you did 412, or if you have your notes on 412, you will notice that you will have to keep referring to some of those notes in regards to certain elements of the control system. So 412 is a very, very important course for you. So I'll assume that you successfully went through that course, and so you're able to use the concepts that you learned in that course here. Okay. Now, again, there are certain reading materials that you can check. These days, you can get a lot of materials online, and you can use them to study on your own and also just sharpen your skills and prepare for the class as well. So in control systems, we have very revered books that are very historically preferable amongst those who study control systems. And one of those books is the, let me just indicate. And this is for those who probably would want to focus on finding books and studying them on their own. Of course, you have this book, Automatic Control Systems. Automatic Control Systems. You already know who I'm talking about, by Benjamin C core, I think so. But we just usually call it core. So if you can get a hold of this book in its latest version, I don't know whether it's in its 9th edition or 10th edition, maybe even, I don't want to write the edition because I don't want to restrict you to that. Get the latest edition that you can and use it. It will help you a lot. We also have Modern Control System, another book that I've used in this course, which is very important. Modern Control Systems. This is by Katsuhiko Ogata. Katsuhiko Ogata. There is maybe two more. We have Control Systems Engineering, another very nice book, Control Systems Engineering. This is by Nagrath and Gopal. I think I'll just write Nagrath and Gopal. So if you can lay your hands on either of these books or even all of them to help you reference, it's very important. So I've given you a book by an author from Japan. I've given you a book by an author from Benjamin Sikuo from Europe and then from India. There is another one, Modern Control Systems. This is another very nice book for those who will be doing control systems a lot. Modern Control, it's Modern Control Systems, yes. Modern Control Systems by Richard, I think it's Richard Doff. Richard Doff and R. Bishop. I think both are Richard. Let me just write Bishop. So these books, ladies and gentlemen, you will see are very, very important in providing illustrations, in providing you with worked out examples, in providing you with sample questions. And so it is important that you get a hold of this book after the class and get always, once we discuss something in class, just try and solve the problems provided in these books, you know, and some of them also have solutions. So that will help you to get a proper understanding of this concept. Good. So now that is the initial part of our class. Again, remember 412. You are going to need it, especially on where you are doing a performance analysis, where you are looking at the performance of control systems such as the transient response and the steady state response. That topic is very, very important. So I hope that will sink in. If you need a more elaborate course outline, then please speak to your class rep to get them from the admin, because they should be available to the students. If I remember, I'm also going to append it on the set of notes that I will provide through your class reps. So anyway, before we go to root locus, today's class, I wanted just to introduce, because I want to go straight to root locus. But before I do that, I just need to sort of like do an intro. Because it's important that we remember a lot of the things that we have covered before that we might have overlooked, or that we need to, you know, recap, so that when we go to root locus, it becomes very, very easy to understand the concept. Now, like I said, I do not have this set of notes, so I encourage you to make short notes on your own as the lecture continues. Now, just like you've done before, especially in fourth year, control systems, you must have noticed, is a very, very fundamental topic in engineering. And the reason why control systems are fundamental is because they enable automated processes in various industries. So control systems can be used in various industries. And that's why it's very important to cover. You currently see it, especially even if you watch the news and stuff like that. Control system, and this is precision control systems. We use them in aerospace systems. Okay, if we want to go to fly or even go to the moon or even visit certain planets, extraterrestrial planets, we need to design our systems, but control systems is what will help us do that. In another industry, which again you'll see for those who have gone for attachments or at least visited industries, you'll see that control systems are critical in the manufacturing industry. Not only that, it is also important in robotics. Okay, and not just robotics, we can actually just say automotive processes. Automotive processes. You know, car industries and stuff like that. Because remember, these days we are building, or at least people are trying to prefer either electric vehicles or self-driving vehicles or more smart or intelligent vehicles. And a lot of control systems engineering goes into the design and development of these kind of systems. So the reason why control systems are used in almost all these sectors of our life is because they help to regulate the behavior of dynamic systems so that you achieve a desired output, despite the fact that we have a lot of disturbances and we have a lot of uncertainties. Therefore, the goal of a control system is to adjust the system's inputs. In fact, let me just write the goal of control system, because this is a very important point in order to introduce the reason why we have to analyze systems and design them using some of these techniques that we are talking about, is to adjust let me say, it's to adjust the system's inputs, to achieve a desired performance. So to achieve desired performance. And when I say to achieve desired performance, the desired performance can include things like stability. So you want to achieve stability, that is one. You probably want to achieve speed. That's another thing. You probably want to achieve accuracy. So this is the motivation. You probably want to achieve efficiency. So these are very important performance metrics that enable us to use a control system. Because one, you want your system to remain stable. Okay, there are certain processes that stability is fundamental, and most control system stability is a fundamental aspect. Or you want to achieve a certain speed. Okay, maybe you're manufacturing and you're trying to ensure that you maintain a certain speed in production, or even you're designing an aeroplane, or at least, or you're trying to make sure that you design a device that will attain a certain speed for a long period of time, or regulate speed. You want to achieve accuracy, especially with things like the design of robotics. You know, if you want to design a robotic arm, for example, and you want to achieve 3 or 4 degrees of freedom and stuff like that, the accuracy is very important. Because otherwise that robotic arm will not work well. And then you want to achieve things like efficiency. This happens a lot in manufacturing industries, where you want to use the minimum cost of production, but get the most out of your production. So efficiency is very key. So control systems cannot be done away with. Think about another example that just came into my mind is a thermostat system, for example. So a thermostat system is a control system. So what it does is it adjusts the temperature of the room by regulating either the heating part or the cooling part of your equipment. So that's an entire control system. So because it is automated, based on the room's current temperature, it will be either adjusting the heating or the cooling, such that if it's getting cold in the room, it will start providing some heat. And if it becomes too hot, again, it starts cooling the room. And so that is what a control system is. In automotive systems, like in the car industry, for example, these days I see a lot of cars with adaptive cruise control. Okay, so what that does is that you have a control system. That's why it's called adaptive cruise control. It is a control system that maintains a set vehicle speed by automatically adjusting the throttle inputs. So it will, you're doing nothing. You actually just seated there and it is cruising at a certain preset speed. And it is able to do that on its own because it is a control system. So this is the importance of control systems that if you haven't been exposed to before, then I'd really like that you remember. So in engineering, control systems are very important. And in engineering, we want to achieve things like automation, we want to achieve efficiency, we want to achieve precision, or what you can call accuracy. We also then want to achieve, if I don't forget, sorry, we also want to achieve things like safety. This is also a very critical area these days, safety. So in processes like chemical plants or even in the aviation industry, you need control system to ensure stability and safety so that you react very quickly to potential hazards. Okay, now I have been talking about control systems. Again, remember, I'm using the first hour to just sort of bring you up to speed with control systems because it might have been a long time and we've forgotten a lot of stuff. You remember again, this I hope you do, the basic components, because I'll be referring to this a lot, and when I do, I expect that you understand what I'm talking about. The basic components of a control system. The basic components of a control system. Again, actually, the best thing is to draw it, because writing is becoming too much. So the basic components of a control system. Remember this diagram, very famously drawn. C of S. It's a unity feedback system. There's an error part there. So basic components, and this is how to remember the basic components of a system. So the basic components of this system are, you need the controller. So this is the controller. You need the plant. This is the plant. You need a feedback, or what we famously call a sensor. And of course, you have the feedback loop, which is the diagram that you see there, the feedback loop. And that is denoted by, you see how we feed back into the system. So that you receive an error signal somewhere here. And based on that error signal, the controller, which can be one of many, and again, please, I want to believe that you did this in 412. If you did not, you'll have to go back because I cannot discuss this here. Again, when I talk about the controller, we have the proportional controller, we have the proportional plus integral controller, we have the proportional plus derivative controller, then we have the proportional plus integral plus derivative. And this is what we are going to use a lot, which is just a combination of the proportional, the integral, and the derivative. Please remember that the integral controller is not used on its own, neither is the derivative controller. So the proportional controller, you also need to know, when do you apply PI controller, when do you apply the PD controller, and when do you apply the PID controller, okay? Those are very critical things. And then what is the performance, or when you use the PI controller, what actually are you looking for, okay? When you use the proportional plus derivative controller, what adjustments can you make, okay? So these are some of the things that I expect that you go back to and just refresh your memory in regards to controllers. So the controller is basically the brain of the control system. So when you have an error signal, which is a difference between the desired set point and the actual output, there's an action that needs to be generated by the controller to reduce that error. And I've told you a PID controller is one very common type of controller which is used to make those decisions. So you have an error signal, and based on that error signal, the controller will have to generate a certain action that would reduce this error signal as much as possible, okay? So that we achieve the desired output from a set point, from an input that is given. Of course, the plant is the system or the process that is being controlled. The reason why we have introduced controller, and I hope this was taught to you, is that plant systems are usually, I call them static, in that we cannot really change them. If you install motors in your company and you want to change the performance of your process, you cannot uninstall the motors and install new ones. So the best thing to do is to connect your plant system with a controller which is adjustable. So you control the performance of the plant by changing the parameters of the controller. Because if you're using a PID controller, you can adjust the proportional constant, the integral constant, or the derivative constant. And the adjustment of each has a certain effect on the error signal. So because you're adjusting the controller parameters, you are in effect changing the plant performance characteristics. And that is why plant systems are used in tandem with the controller, because we cannot directly change an installed equipment. For example, if you go to a hydroelectric generating company, they already have the generators installed. They have the shafts already pre-designed and installed. So if they want to improve the performance, or at least if they want to change the process, the characteristics of their plant system, they cannot be uninstalling the equipment to do that. They only need to connect the equipment with a controller, which then allows them to adjust the parameters of the controller to affect or to effect the characteristics, the performance characteristics of the plant. I hope that is very clear. And if it is not, please let us just go back and study that. Again, because my hour is almost up, the sensor part, of course, is just a measuring instrument, because here you can have, this is where you measure the current state of the output system. The sensor measures the current state of the output system. That means it can either be a speed, you're measuring maybe temperature, you're measuring maybe pressure, okay? So, and then you send this data is actually sent to the controller. So the sensor helps you to provide real-time feedback, especially for this closed loop system. That's a very, very important aspect. We have a closed loop system like that. So again, I was just bringing this up to remind you that we are going to be referring to a lot of these components of the control system, and therefore it is important as a student to have this at the back of your mind, especially in the use of the PID controller. This will even extend in the second semester when we are talking about industrial automation, where we're introducing PLCs. But PLCs will be introduced after I have introduced, again, PID controllers. Because PLCs are just like PID. They're also controllers like PID. That's why it's called PLC, Programmable Logic Control. The PID is also a controller because it's a proportional plus integral plus derivative controller. So all these are control mechanisms that you must know. Now, if you remember our discussion here, I said the main goal of a control system is to ensure that we adjust the system's inputs to achieve a certain desired performance. And one of the performance metrics that I mentioned, in fact, the first one, is stability. So allow me, ladies and gentlemen, to emphasize or re-emphasize the need for stability in systems. Remember, this is simply a recap to introduce you to the need for root locus analysis. Now, stability is a very crucial metric in control systems. So a system is stable if its output remains bounded, over time when you subject it to inputs. So that means the output is predictable over a period of time. Then that means the system is stable. Remember, when you are plotting those performance metrics, if I gave you a system whose performance is like this, then you'd say that the system is stable. If I gave you that diagram, then you say that that system, of course, stabilizes after a period of time. But if I gave you this, then you'll say this system is unstable because it is not bounded. You can see it goes to infinity. It's not bounded over time. But at least this one is bounded over time. You can see that this is bounded over time. This is bounded. Okay. So stability is a very, very critical metric that we are looking at, because in unstable systems, outputs can grow uncontrollably. If we let the systems be unstable, like in this case, then the output is uncontrollable. And when the output is uncontrollable, it leads to system failure. It can also lead to unsafe conditions. Okay? So engineers ensure stability through various techniques because stability is key. One of the reasons that you might have encountered before, especially in 412, is either through pole placement, okay, where you had said if a pole lies on the left half plane, then the system is stable, or we can use what we call gain tuning. We tune the gain of the system. Don't worry, I'll bring that again later. Or we use feedback loops. Feedback loops. And that's what I told you here, that if you have an error signal because of instability, then your feedback loop through the sensors will make sure that that signal is fed back into the system, and the controller will try to reduce that error signal up until the point where your output is now desired. When the output is desired, it means it is controllable. Again, at the tail end of this course, we will see how to test whether a system is controllable or not. Okay? You can test that too. So stability is critical. Of course, I had mentioned things like performance. Okay? In terms of speed, accuracy, And this is where, again, in performance, this I will not do. This I promise you I will not do. I will want you to do it on your own, especially when I had introduced the PID controller. When I talk about performance, I'd mentioned either, because this you did in fourth year, either we are talking about transient or steady state. Okay, so these are the things where we are talking about settling time, overshoot or maximum overshoot, rise time, rise time, and those things. Steady state error is where we are talking. Steady state response is where we are talking about the steady state error. So these things I expect you to understand. I'm just bringing them up so that as you study, you of course remember what to focus on. Okay? Please remember that designing a control system involves balancing these performance characteristics while ensuring stability, because that's the focus. The design focus is on achieving stability and of course performance. But the first thing is stability. So stability is key because it is affected by several things. Like I was discussing here, stability is affected by things like, and I gave you the methods that you can use to achieve stability, but you must also understand what brings about instability. So let me just indicate here instability. The causes for instability. The main one, of course, is uncertainty. I'm almost going to my second hour, but anyway, so in uncertainty, for example, here is where the actual system might differ from the mathematical model. So you had modeled your system using mathematical expressions, but the system is a little off from the model, especially during design. So here you have unpredictable behavior. Unpredictable behavior. And like I say, the reason for the unpredictable behavior is because the mathematical modeling of your system in your design is not the same as the actual system. When you do your final year projects, you will see a lot about this, especially those who do their own design, is that you'll come up with mathematical expressions to design a certain, a certain phenomena. But when you actually implement it, you see that there's a variation. So that unpredictability is one of the reasons for instability. Okay. The other one is what's the other one? It's non-linearities. Yes, non-linearities. Non-linearities. Because, ladies and gentlemen, in real world systems, we have non-linear components. I know in class we do a lot of linear analysis. That means we simplify our mathematical expressions or equations by assuming that the system is linear. But in real world, systems are not linear. Even Ohm's law is not linear. Okay, so because real world systems are non-linear in nature, then that complicates the control design, and therefore it leads to instability if not properly handled. So non-linearities also bring about instability. The other thing that brings about instability, and this should be known to any engineer out there, is what we call disturbances, aka noise. Noise. So these are external elements, external disturbances or sensor noise, because sensors are never 100% accurate. They have an element of noise in them. And again, as engineers, when we say noise, we don't mean somebody shouting. I hope we understand that. We must be able to define noise. A noise can actually be, it's a signal actually. If you look at it through the oscilloscope, you can actually see that it is a signal. It can be a sine wave. okay? But the very nature that it is unwanted, it exists in an area where it is not wanted, then we regard it as noise, okay? So external disturbances or the sensor noises can also impact the performance and the stability of system. So it's very, very important that we consider noises when we're doing our designs. So in order for us to achieve stability, sometimes we might be required to compromise on speed or on accuracy. So as engineers, when we do our design, there's usually a trade-off between stability and performance. So, and that is why we are engineers. That's why we do design. We look at what is the best case scenario, what is the worst case scenario, what trade-offs can we make so that we get a system that, yes, is stable, preferably as expected. But deep down in our design, we know that we must always sort of sacrifice performance for stability. It is never the other way around. We never compromise on stability to achieve performance. Usually, we compromise on performance factors, things like speed, accuracy, responsiveness. So you would rather build a less accurate system, but it is more stable, rather than building an unstable system that is very high, that is highly accurate. That is why all systems, even a resistor, comes with a margin of +5. They tell you the margin is a +5% or a plus or minus 5% of resistance, for example. Meaning, in order to ensure that that element, that component is stable, they can actually decide to compromise on its accuracy. Even sensors, the reason why they are not 100% accurate is because a trade-off has been made between stability and performance. That's critical. So again, I cannot overemphasize that point. Now, let me bring you back, because I said when it gets to 8 o'clock, I mean 9 o'clock, I discuss root locus. Remember, this is just an introductory class, so it's a lot theoretical, but in subsequent classes, we actually are going to be doing a lot of calculations. And before I forget, by the way, from the next class onwards, please make sure you have a calculator with you and you're able to carry out certain calculations. So you must have a notebook, a pen, and a calculator. Otherwise, you will float all the way. That's why I told you there aren't so many notes for this course, but there are a lot of calculations to be done and a lot of drawing to be done. So you should be able to do those as we go along. But because I'm just introducing these elements, it's going to be theoretical in this class. Now, how do we, again, please let me take you back just to remind you, I said there are certain ways in which we can achieve stability. And the first one, I said we can use pole placement, gain tuning, or feedback loops. The one that I want us to focus on, and the not really one, the two that we'll be looking at when we're doing root locus is both pole placement and gain tuning. That's very important. So how do poles help us achieve stability? So let me just say stability using pole zero plots. Again, just to introduce you to this, then we go to root locus. So a pole zero plot is just like that word. It's plotting poles and zeros, meaning looking at or indicating the location of poles and the location of zeros. So pole zero plots will provide you with a graphical representation of poles and zeros of a system in a complex plane. Please, again, if I don't, please don't forget about the complex plane, the real axis and the imaginary axis. That's a complex plane, otherwise known as an S plane. Because in all our analysis this semester, this is the plane that we are going to use to plot our poles and zeros. So please remember poles and zeros on a complex plane. And I've said, like we have agreed before, that the reason why we are doing this is because we want to achieve stability. So we need to visualize. As engineers, we must visualize the system's stability response characteristics by the location of the poles and zeros. Now, poles represent points where the system's transfer function becomes infinite. In fact, let me just write, poles represent, because we usually just we put an X, but we don't know what that means. Poles represent points where the system's transfer function becomes infinite or tends to infinity. Okay? Zeros represent points where the transfer function becomes zero. That is why, ladies and gentlemen, we usually have a transfer function, let's call it G of S. It's usually having a numerator term and a denominator term. Now, we always know that we can actually say it's usually composed of some zeros in the numerator and poles in the denominator. So the fact that this is just an example. So the fact that we have zeros in the numerator, let me actually just put Z's and P's, okay? We'll change that later. This is just for illustration purposes. So the poles represent points where the systems become infinite. And the zeros represent points where the transfer function becomes zero. Okay? So in these plots, poles in the left half, okay, let me remove this S plane for now. Poles in the left half of the complex plane indicate stability. So if poles, because we usually represent poles by X's, okay? So whether they fall there, or even here on the line, then that represents stability. So if poles lie on the left half of the complex plane, we indicate stability. But it's not just that. This is very, very important. And please pay attention. The closer the poles are to the imaginary axis, the slower and less damped the system responds. You know that you always, when you are discussing 412, we were talking about stability in three ways. We were saying that the system is stable, or it was marginally stable, or the system was unstable. And all this was in reference to the location of the poles. So here, the poles were lying on the left half. We know that the poles are on the left half, sorry. So poles, let me just say, poles are on the left half, okay, of the complex plane. When you ascertain in your design as an engineer that the poles of your system, the poles that represent points where the system's transfer function is becoming infinite, if they lie on the left half of the complex plane, then you say our system is stable. Now, those poles could also be moving towards the imaginary axis. So if the poles are closer, the more they get closer to the imaginary axis, they can get as close as possible, up to the point where maybe, let's say it's somewhere there, or even another one somewhere there, as close as possible, or even lie on the imaginary axis. Then we are saying, if you look at the performance, not the transient performance, you'll see that the system is less damped. And therefore, see, this is damping. This is where you, again, I take you back. So which system is over damped? Which system is under damped? You know, where you calculate damping ratio and all that stuff. I said I'm not going back there, but I'm just bringing your thoughts towards that. So when your poles are towards the imaginary axis, it means our system is actually becoming less stable. That's what we're trying to say. Our system is becoming less stable. When they are on the imaginary axis, then the system response becomes slower. So it is less damped. And when it's less damped, it means the instability starts coming out. The instability is you start seeing instability as the poles moves towards the imaginary axis. Actually, when they are on the imaginary axis, that's why we refer to them as marginally stable. Here, poles lie on the J omega axis. So our system is marginally stable. Any movement to the right, now that leads to instability. So here our poles are in the right half. Poles are in the right half of our J omega, of our S plane, of the complex plane, the right half of the S plane. So the system here is actually unstable. And when the system is unstable, we say it means it has what we are calling unbounded. We have unbounded outputs. Unbounded outputs. Meaning the outputs don't have a boundary. They are uncontrollable. We cannot predict the behavior of the system with time because it is unbounded. This is unbounded. We cannot know what next. Okay, we cannot predict what next. Here, it's easy to see how the system is going to behave. It's actually stabilizing. It's damping nicely. Okay, even here, it's stable, but here it's unstable. So it's very, very important for us to know the types of stability that we are talking about. And so, ladies and gentlemen, with this kind of introduction, this is what leads me to the famous root locus. We have understood what control systems are. We have talked about the elements or the components of a control system. We have seen that there are certain key elements of any control system in terms of achieving stability and performance. We've seen areas where you can do a compromise between stability and performance. Actually, you compromise performance for stability. But we have also seen the types of stability that you can achieve and how you can use the poles to achieve that stability. In essence, whenever any engineer is doing a design, it is important that they plot some graphical representation to visualize the system's stability so that you don't end up coming up with your design, implementing it, and then that's when you realize that your system is unstable. It is at your design point that you should be able to visualize whether your system is going to be stable or unstable. And you can make changes at the design level. And one way to do that is to have a graphical representation of your system, of the poles and zeros of the system that you're designing. That will help you visualize whether the system is going to be stable and even visualize the response characteristics. the transient response and the steady state response characteristics of your system. You can visualize that at the design point. And that is what brings me to a very, very important tool known as the root locus. So what is the root locus? The root locus is a graphical. This is very important. That's why I told you the complex plane is going to be our plane of plotting. It's a graphical method used, let me say, in control theory to analyze, very important, to analyze how the poles of a system change as a particular parameter, and this, in this case, let me just put it in bracket, usually gain, verify that gain K varies. This is a very, very important definition. Now, I have been quiet, I mean, it's been very quiet in this class. Again, can just anyone tell me that I'm still with you and you can still hear me?
Yes, we can.
Good, thank you very
Yeah.
much. So this is a very important definition. And I'm going to give you the key points of this definition so that you understand it. But let's look at the definition again. That our root locus is a graphical method. So there's going to be a lot of plotting. Now we can either plot manually, which we have to do in class because we are students and we are learning, but we can also use tools to plot, tools like MATLAB or Python to do these plots. But those computer tools can be used later, especially after you've understood how root locus works. To understand how root locus works, it's best to start by plotting manually. Then later you can move on to MATLAB and Python and so on to help you figure out more complex plots. But for simpler plots, you can just use a manual plotting method. After all, in the exams, you'll be tested on the manual plotting. You'll not use any of those computer tools. But in a lot of your work later on, you'll notice that you'll need things like MATLAB to help you do root locus plots. And it's very easy to plot. I will actually take time to show you some of this and give you some of the commands, and then you'll go and see some of those plots. I'm sure, again, you've handled MATLAB, yes, I remember from the 4th year lab. So I know that you should be able to do this very easily. Now, the key points here, please note, we are plotting graphically the behavior of the poles, not zeros. But it does not mean that zeros will not be plotted. No. We want to analyze how the poles of a system change. Now, mark my words. In analyzing the poles of a system, they change based also on the location of the zeros, because a transfer function does not only consist of poles. We said a transfer function, g of s, consists of a numerator term where we usually have the zeros and the denominator term where we have the poles. So the change of the poles is also affected by the location of the zeros. So our graphical representation usually is a plot of both the poles and zeros. But the zeros helps us to just know how the poles behave. And we'll see that as we start plotting. But it's not just the movement of the poles in regards to the presence of zeros around them, but also as a particular parameter is, there are so many parameters that you can keep changing in a control or in a transfer function to ensure that the poles move. But the one that we are interested in is as the gain varies. So what I am saying is we will probably have a system where you have a gain, then you have your zeros, then you have your poles. Okay? I'm just giving this as an example. So in our plot, we must consider the movement of the poles in relation to the position of the zeros, but as this gain is also varied. So that's very critical. And that's why that definition is complete as is. That we want to analyze the change, I mean, the how the poles will move or how the poles behave in our system that we are designing. But we know that, of course, that would be affected by the location of the zeros. It usually is, and you'll see that when we are using, when I give you the rules of plotting a root locus. But usually the parameter that we're interested in this course is gain. There are other parameters that can also be varied to change the pole positions, but we are interested in changing the gain. So in fact, other books will say as gain k tends to infinity. So because gain has to start. Now, gain can be, again, I think it's important I mention at this point, that gain can be from minus infinity to infinity. But because of mathematical simplification, and because we are only using this to illustrate how you can use a graphical method like root locus to design your system for stability, we'll restrict our gain from 0 to infinity, not from minus infinity to infinity. Just like in Laplace transforms, we could do it from minus infinity to infinity, but also we could also just do it from 0 to infinity because one replicates the other. So our analysis in class, our gain is always going to be from 0 to infinity. But in real life, gain can be from minus infinity to infinity. So don't fixate your mind on a very specific limit of gain. It can be from minus infinity to infinity. But for our case and for simplification purposes, we'll consider 0 to infinity. So the key points from this definition, that's why I'm still on this definition. The key points are as follows. One, this definition shows that the movement of poles in the complex plane, especially as gain k increases, the gain k will be increasing from 0 to infinity. So the root locus, so let me just write, the first point is that the root locus, I'll actually keep referring to it as RL, the root locus shows movement. This is very important. If somebody asks you, a lay person asks you, what does root locus do? It shows movement of poles in complex plane. Okay? As gain k tends to infinity. I'm trying to shorten my words now as much as possible. So it shows the movement of poles in the complex plane as gain k increases from 0 to infinity. Number two, it is also important to note from this definition that by analyzing the root locus, we can determine how changes in gain will affect the system stability and performance. And we are going to do that. So from the RL plot, okay, we can determine how changes in K, okay, affects how changes in K affects stability, and not just stability, but also performance. You can do that, okay? But I'll be focusing more on stability. What I'm trying to say is, like I've asked before, and I might ask again in future, I might ask you, what is the range of the gain K that ensures that your system is stable? So you'll tell me, based on my system, I've calculated and I've noticed that my K must lie between maybe 0 and 150. That is the range of my gain K where the system is stable. Anything out of these boundaries, then the system becomes unstable. So therefore, and you can determine this from the plot, of course, in combination with the famous Ruth Howie's criterion. Okay, so again, we will do that as time goes on. But what is important is your root locus not only shows you the movement of poles, it also tells you the range of the gain K that ensures that the system is stable. You can even go ahead and it can tells you, it can tell you areas where there exists an overshoot and stuff like that, where you're now looking at the transient response. But that's not my focus in this study. So it is especially useful for designing feedback control systems, because it will be providing insights on how to tune the gain for some desired performance while ensuring that your system is stable. So the root locus vary the control parameter. The control parameter here is K. And this, in general, of course, will aid you in providing a design of a stable and well-performing system, because that's what you must be able to do. As you design, you need a stable system, but also a well-performing system. In order to do that, you can use a visualizing aid like root locus to give you a clear understanding of how the behavior of your system changes as you change the gain K, or as you control one parameter, in this case, K. So it's very, very critical for us to understand how root locus works. So I would like to mention at this stage, because I fear, and usually this is my fear, is sometimes I go back a lot to explain certain concepts because I want us to understand the concepts that I'm about to introduce. But in my process of doing that, I usually sort of digress a lot, and then we might not be able to cover what I need us to cover. But I'll try as much as possible to be disciplined. The only reason I'm doing this is because from the history that I have with students, I know that there are certain critical areas that if I do not touch on, then they're going to be floating for the rest of the session, which I do not like. So it's important that I mention, even in passing, certain key concepts, so that even when you're reading, you sort of meet them, and then you understand that, oh, he spoke about this, so maybe I should understand more, read more about it. So allow me again to just talk about something very little, then we now go to the real root locus. At least I have justified why we need root locus. So actually, next time if I ask you a question like, what is the significance of root locus in the design of control systems in engineering? You should give me at least two reasons signifying the need for root locus in designing control systems in engineering. Okay, so let me look at something here. Control systems, poles, and stability. Because if we don't understand this, then our plots are not going to mean much. We have mentioned that in control systems, the poles and the zeros are key concepts that are derived from the system's transfer function. You'll get your poles and zeros from the transfer function. But these poles and zeros represent a mathematical relationship between the input and the output. So poles lie on the denominator that I have told you of the transfer function, okay? Meaning, because they make the denominator of the transfer function 0, it means that they cause the system's output to become infinite. Poles, I've also said, are critical in determining the system's dynamics, that is stability, and even response characteristics. Zeros, on the other hand, we've said their values, they appear on the numerator of the transfer function, okay? causing the output to be 0 for certain inputs. But the zeros influence, the influence of zeros, is especially on the frequency response of the system and even the shape of the system's output. We will plot that, and you will see when I move zeros, you'll see how the poles behave. And when you move poles, and moving them, I mean as you move them towards, the reference point is the S-plane. So are you moving them towards the imaginary axis or away from the imaginary axis? And you'll see what happens. And we've also mentioned that poles have a direct influence on the transient response and steady state response. Transient response is where, for example, we say the location of poles will determine how quickly the system responds to changes. I have just mentioned to you a few minutes ago that when you move a pole towards the imaginary axis, then it means the system takes longer to respond. Again, that means it now might become unstable. It starts to become unstable up to the point that it crosses the imaginary axis, and then now instability checks in. So poles closer to the origin or on the J omega axis results in a slower system. But poles that are farther away to the left indicate a faster response. And you know, that is a response characteristic. Okay? Complex poles, and that means complex poles are poles like this. So if I had a pole, and again, notice that every time I draw an S-plane, I label it. Because if you don't label it, it can be a Cartesian plane. And ladies and gentlemen, you know that the difference between these two is very minimal. So if you plot for me, if you say this, I will not take it as a complex plane because I can decide this is X and this is Y. Now we are on the Cartesian plane. So please make sure that you use the proper labeling to show that you are actually on an S-plane. In fact, some books or even some people will insist that aside from drawing it, you must also indicate that this is S-plane to just confirm. So poles, complex poles are poles like that exist. They have both the real and imaginary parts. And these complex poles usually lead to oscillatory behavior. And when you say oscillatory behavior, it's a system like this. I think I drew it somewhere here. This system is oscillating, this one. And when it's oscillating, it means what we are simply saying, it influences the overshoot and even the damping. Okay? So oscillations are never desired especially in control systems that oscillate, unless it is controlled oscillation, which again is a subject for another study. But please remember, transient response is affected by the location of the poles. If the poles are far away from the origin, then the system responds faster. If they are closer to the origin or the J omega axis, then the system becomes slower. That's affecting a response. There is also steady state response. So if you have zeros and even other, not just zeros, even there are certain factors that can impact the system's transient behavior. But poles will primarily determine the long-term behavior. Okay? For example, you can say a system is stable if its output settles to a constant value after a disturbance. And that is governed by the pole location. What I mean is this, for those who are visual in nature. Let's say I introduced a disturbance here. So you can see this is a disturbance. You see that oscillation there? That's a disturbance. But shortly after that disturbance has been introduced, you can see what's happening. The system dumps itself, and therefore the output is settling. It settles after a disturbance. So you can actually calculate that parameter, and it's caused by the pole locations to ensure that even if you introduce noise or a disturbance, the system is still able to quickly settle back after that disturbance. So the location of the poles is very important, and we have talked about that. So I'll go back to root locus. Pardon me, I have been talking too much in other fora, so sometimes my voice gives way. But I hope it will not affect our study today. So again, please remember that it is important for us to understand the location or the movement of the complex poles, and also the movement of the real poles, those that lie on the real axis, because this is the real axis and this is the imaginary axis. Okay, that's the real axis and that's the imaginary axis. So now I want us to go back to root locus. So now we start our class. We are done with just the intro. We are actually now on the real class. So for the next, let me just take about 20 minutes, then I'll let you go. We'll continue the class tomorrow. But I need to do this because it's also part of just introducing root locus, because we can go into root locus real tomorrow. But now I just need us to discuss one or two things that can also help us in our study of root locus. Remember, we lost 2 weeks, so I'm trying to push as much as possible. The other tool that we are going to need, ladies and gentlemen, that's very important, and again, I ask you to go and read about it, is the vector representation. This is maths. You've done it. Vector representation of complex numbers. We are going to do this a lot. Vector representation of complex number. We've just told you a complex number. We are having J S equals to J omega. Okay. So what I mean is, if I drew this, I'm now introducing a little bit of maths because we are also going to need this a lot. And I say, this is the real axis. This is the J omega axis. Okay. I can even say this is the S plane to just make sure that it syncs. And then I draw a vector. So let me draw a vector here. Like that. When I draw a vector there, it means that there's an angle that it makes with the real axis. Let's call that angle theta. Okay? Let's call the magnitude. Let's say the magnitude of this vector here is m, and it makes an angle of theta here. Okay? That is when we now represent this S-plane as that. Okay? But in vector representation of complex numbers, you remember we have two forms. You have the rectangular form, which is this. Again, I'm now back to teaching maths. But we also have the other form that we prefer, and we call it the polar form. It's not wrong to use either of these forms. It's fine. But the polar form will help you in certain areas that the rectangular form will not. There are certain times when you want to add vectors, you can actually just use rectangular form and do your additions, the real parts and the imaginary parts. But when you want to multiply vectors, the rectangular form is tedious, but you can use polar form, because in polar form, the rule for multiplication is simple. You multiply the magnitude and you add the angles. So that becomes easier. And the polar form is this form, where now it's the magnitude, angle, theta. So there are certain manipulations where the rectangular form is preferred, but there are others where the polar form is more reliable. Okay. So again, ladies and gentlemen, please, if you have forgotten the use of vector representation in complex numbers, please go back and check what your rectangular manipulations are and your polar form manipulations are. If still that doesn't make sense, I have one example here. Let's do one example here. Very important. I'll even set this in the card. Let's say given, let's give an expression, given, let's say a transfer function, g of s. Now we are done with theory. We are back to real stuff now. Given a transfer function, let's call it g of s. It consists of a 0. Let's say that 0 is s plus 1. And we have some poles. Like that. And I ask the question. Let me ask the question. The question is, find g of s at the point s equals to minus 3 plus j4. Typical question. Given a transfer function g of s, find g of s at a specific point minus 3 plus j4. Now, the rectangular form would tell you that what I have to do is, you're asking me for g of s at minus 3 plus j4. So one way, which I'm not going to use a lot because it will not be helpful in other areas, but you can still use it. I'm not disregarding it. That's why I'm actually putting it as an option. So actually, let me call it solution 1. We say g of s, sorry, let me use a different marker. G of s at s equals to minus 3 plus j4 can also be said to be g of minus 3 plus j4. Okay, so what I'm simply doing is substituting for s. So g of s, and s is minus 3 plus j4. Alternatively, I can write it as g of s at s equals to minus 3 plus j4. So if I use this method, then it means where there is s, I have to put minus 3 plus j4. So I'll be having minus 3 plus j4 plus 1 over minus 3 plus j4. You see that? Then s, no, sorry, again, I'm confusing myself. Minus 3 plus j4 plus 2. What I've done, ladies and gentlemen, is because I've been asked to find g of s at the point s is minus 3 plus j4. So wherever there is s, I substitute it with minus 3 plus j4. If I do that, and please, you'll help me on this because I don't have a solution to this. You will help me, and don't let me mislead you, especially in calculations. It's wrong. So this therefore would mean our solution is, of course, minus 3 plus 1 is minus 2. So we'll have minus 2 plus j4 in the numerator. Please do this with me. If I'm wrong, you correct me because I don't have the solution. Minus 3 plus j4. But you'll have to multiply it with, I think this is 1. Minus 3 plus 2 is minus 1 plus j4. Minus 1 plus j4. So therefore, it means you will have to multiply this. I'm sticking to rectangular form. You'll have to multiply out the denominators. And you know that when you multiply j's, it's going to be minus 1 and so on and so forth. You do your manipulations, and then you'll find an answer there. But that answer is still going to be in rectangular form. Now, you're required to find f of s. So your answer here, if you do your manipulation here, your answer is going to be in rectangular form. Once you get your answer in rectangular form, you can actually convert it back to polar form and vice versa. My point here is this. Whenever we have division of complex numbers, rectangular form is not the best form to use. Rectangular form is best when we are doing addition and subtraction. But multiplications and divisions of complex numbers are best manipulated in the polar form. And to prove that, because I cannot do this, this is going to be tedious. Somebody can try it out. I'm sure you'll get to the answer. But after a lot of manipulations, you can try that out. But imagine if I was to do this. So let's say I gave you 3 marks. Yes. So this question is 3 marks. This manipulation can take you time, and chances
Excuse-
are, yes.
Sorry, kindly can you repeat the statement on which is favorable for rectangular and which is favorable for polar form? I want to know something.
No, I shouldn't even be saying this. This is a skill that you probably needed to have learned in maths. What I'm trying to say is, whenever you are adding complex numbers or you're subtracting complex numbers, somebody has said 3 plus J4 added to 6 plus J. This addition is straightforward in rectangular form, in the form that it is, because all you have to do is add the real parts. You get 9 plus J5, and you're done. Very simple. You can even convert this to polar form, and you know how to do the conversion, because you'll be having 9 squared plus 5 squared square root. You get the magnitude. That's what I'm saying. But that's not important now. What's important here is manipulations that require additions and subtractions of complex numbers are best done in rectangular form, because you can see how straightforward it is. Even if I was to subtract, it's still just rectangular form, and I get my answer very quickly. But manipulations that require division and multiplication of complex numbers. So I have 2 plus J5 multiplied by 3 plus J8. Or even division. So maybe divide by 2 plus J. You can do this in rectangular form. It's going to be tedious. You're most likely going to make a mistake somewhere in the manipulation, and that will cost you. It still works, but you have to be extra careful, and you have to actually check your work properly. But if I change this to polar form, in polar form, this becomes very easy. I'll tell you why. In polar form, I'm not doing the exact thing. I'm just doing an illustration based on the question the student has asked. So in polar form, I might find I can convert, because conversion these days, you've got calculators that converts those things for you instantly. So I might convert 2 plus J5 into polar form. And I don't know what it is, but you can tell me 4 plus 25 divided. So you'll get a value. So let's say you get a value for the first one. If I convert this to polar form, let me say I find 6.1 angle 30. I'm using this arbitrarily. This is not the solution. Multiplied by this one. So let's say this one is now 7 angle 20. Notice I'm putting the angles in degrees so that you know it is an angle we are talking about. Then this one, maybe it's 1 angle 15. So now see, the manipulation of this, now this is polar form. It's a polar equivalent of the first question here. So this is this is now the polar form. The manipulation of this polar form, solving it becomes very easy, because the rule is always very simple. That in polar form, you have a magnitude and you have an angle. So for the magnitude, you simply multiply those numbers out and divide them out as usual. So for the magnitude part, we are going to have, again, let me rub off some part here, that because we want to use this. So for the magnitude part, we can actually just say that we have M would be equal to 6.1 multiplied by 7. Again, these are not real values. I mean, I just made them up. And then you'll find an answer. So let's say it's 42 point something, I don't know, 42.7. That's the magnitude. In polar form, the angle said, the rule is if you're multiplying out angle, you simply add them, and then for the division, you subtract. So the angle format is simply going to be 30 degrees. Because it's a multiplication, I simply add plus 20 degrees. And here we have a division for the denominator term, so we simply subtract 15 degrees. And therefore, your answer is going to be, again, remember, this is where you, so we'll have 50 minus 15. I think that should be 35, I don't know. So that in polar form, your solution is simple. M angle theta equals to 42.7 angle 35. Very simple. And if you needed it back in rectangular form, again, you simply punch this in your calculator, because your calculator these days has these options. In our days, we had to do this manually, but here you can simply punch in the magnitude and angle, and it gives you the rectangular equivalent instantly. So you can see that this manipulation is easier and is less prone to mistakes than when you are actually multiplying this out, because if we are doing this manipulation manually, then I'll be having 6 plus J16 plus J15, and then I have J5 and J5. J and J should be negative, so that should be minus 40. So you can actually see, and then of course I still have to divide by 2 plus J. So still, I am going to be having difficulties, especially if the complex numbers are a little large, because the manipulations would be difficult. So like I've said, when you're doing additions and subtractions of complex numbers, then it's easily done in their rectangular form. But when you're doing multiplications and divisions of complex numbers, they're best done in their polar form, given the fact that you can always change between one form and another. But the polar form, you can see how straightforward it is, and it's easy to see if there's a mistake, because multiplying 6.1 and 7 is not a big deal. Adding angles and subtracting angles, because it essentially goes back to just adding and subtraction. So it becomes very, very easy. I hope that is clear. Is it clear?
Yes.
Good, thank you. Good. So now let's go back to our question so that I end this class. The question was, you're given this transfer function, and you're told to find g of s at the point s equals to minus 3 plus j4. Of course, you can do this manipulation, okay? But I wanted to show you this because root locus is all about graphical illustration. So you don't have to do this, but because it is a representation that is easily understood, I'll draw an S-plane. Then I'll plot all this, just because this is my intention is purely to give you an illustration. So let's say this is 0, minus 1, minus 2, minus 3. Then you have J1, J2, J3, and so on and so forth. So the first one is a 0. The 0 is at, notice here, it is S plus 1. So the 0 is at minus 1 because S therefore becomes minus 1. I hope that is clear. So you have a 0 at minus 1. So you come to minus 1 and you draw a 0 like this. This is root locus. So that's why I'm trying to show you. I'm just giving a vector representation in the complex plane. So you don't have to do this. To solve this question, we could just convert these things to a polar form and do what we want to do. But I want to show you why we are required to get the transfer function at this point. So we need to know where this point is. So now we have a 0 at minus 1. Sorry. We have a 0 at minus 1. Then we have a pole at 0, because S is 0 here, S is minus 2. So we have a pole at 0 and another one at minus 2. So we have a pole at 0, meaning at 0 here, I have to draw a pole, and at -2, I have to draw a pole. I hope that's very clear. You can see that I'm attempting as much as possible to draw this as is, so that you can see the points. Let me make this clear. So let me introduce -j, and just say j4 there. So we have the 0 at -1 and the pole at 0 and at -2. But we are required to find the point, the g of s at the point -3 plus j4, -3 plus j4. So -3 plus j4 is somewhere here. So we are not told whether it's a pole or a 0. We are told it's a point. So this is the point. This is the point. So find g of s at this point. So the best thing to do is to draw a line from this point, okay, to all these lines of the poles and zeros. So you draw a line from, we draw a line from this point to this, draw a line from this point to this, and draw a line from this point to this, like that. So you have the point, and we know that this line here, this one is for S. Because remember, S, it's this one here. S is 0. And then the second line here for the 0 is for S plus 1. So this one here is S plus 1. And then lastly, this one here is S plus 2. Okay? That's very clear just from the illustrations. So now it's very easy to visualize. That's what I was talking about. If you were doing a mathematical manipulation earlier, and if you're already conversant with this technique, you don't have to visualize. But because I'm introducing you to root lockers, which is a visual aid or a method that is graphical in nature, I just wanted to show you what the location of the poles and the zeros are and the point of reference that we have been asked to find, okay? So therefore, because all these points are terminating at the point -3 plus j4, we can convert, because I told you manipulations on multiplication and division of complex numbers is best done in polar form. So we can say, for example, we can say that the vector, pardon me, let me just say the vector, I'm taking long here just to explain, but when you are to do this on your own, it's very fast. The vector originating, for me, I'm trying to explain, that's why I'm taking long. The vector originating at the 0, yes, at the 0, this 0, at the 0 at -1, because the 0 is at -1, is given by, so you have this 0. So we are saying the vector, remember we have already put it, we have terminated it at the point of desire, that the one we were told is -3 plus j4. So all I have to do is find the magnitude of this line and the angle it makes with the x-axis. But remember, all angles should be measured in the counterclockwise manner, okay? So the angle that I'm really interested in is the angle between this point all the way to this line, okay? So the reason why I need that angle is all angles are measured counterclockwise from the real axis. But I can find, alternatively, I can find this angle here, but then I subtract from 180 and I get it. So you can help me out here because this is now a very easy thing to do. How do I get this angle here? Let me call this angle theta 1. Theta 1. Okay, so you know that theta 1 should be equal to, again, this is some trigonometry that should be very easy. Sorry, you can take, because you're finding this angle here, the adjacent length is 1, the opposite length is 4, because notice it's 4 from here. This is at 4, and so we are looking at this angle here. So mine is simply to say that the vertical length, or what we call the opposite in trigonometry, is actually 4, and the horizontal length, because it's just this small angle that I want here, is 1. So what do we get when we are comparing the it's a tangent, yes, opposite and adjacent. So you have the inverse tangent of 4 divided by 1. This is trigonometry. So somebody can tell me what that angle is, please. What is the inverse tangent of 4? The inverse tangent of 4? Nobody wants to say it. Now I have to look for a calculator. Anyone, please help me?
75.9.
75.9.
75.96.
So this 75.
Yeah.
75.96.
Excuse me, sir.
Yes.
Is the adjacent going from -1 to -2 or from -1 to -3?
You're asking if the adjacent is going from, oh, it's my mistake. Sorry. Thank you very much. The adjacent is from -1 to -3, because we can actually just drop this down here like this, and it's this angle we are looking for. Thank you very much. Sorry, it's my mistake. I think I'm forgetting my trigonometry. So it's actually the adjacent is -2, because there are 2 units here. The opposite is 4. So it should be 4/2. Thank you. Thank you very much. That's why I told you, please don't let me mislead you, because I'm equally human. I'm just guiding you through this process. So what is this angle now? What is the inverse tangent of 2?
63.43.
63.43. Thank you very much. And therefore, because I told you we are not actually interested in theta 1, we are measuring all angles from the real axis. So the real angle that we are looking for this 0 at -1 is 180 degrees minus 63.43, which I think should be, I don't know, 116 point, let me call it 0.6, just rounding off degrees. But what is the magnitude? What is the magnitude? Somebody help me out with that. Your calculations, tell me what that magnitude is. We are looking for this hypotenuse. Hypotenuse, how do we get it? It's root of 20, because we have 2 squared plus 4 squared. That's 16 plus 4, 20. So the magnitude is root 20, and the angle is 116.6 degrees. Okay? I'm illustrating this in regards to the point -3 plus J4. So I'll wrap this off. So at least we now know what to do for the rest of the lines. So please, for those who are wondering how I got this, it's simply opposite squared plus adjacent squared, then I get the square root. That gives me the magnitude of this line S+1, of the line S+1. So that is the vector originating at the 0 at -1. So it's given by that. So we quickly do, because I need to end the class now, can we quickly do for the 2 remaining? We say the vector, this is now quick trigonometry, the vector originating at the pole, the vector originating at the pole, please check me, and the pole is at the origin, at the origin is given by, let's see, the one at the origin. So at the origin, we can actually use the inverse tan to give us that angle there, it's going to be, the angle is going to be the tangent, inverse tangent of opposite over adjacent still. So we still have 4/3, I think. Yes, 4/3. Please tell me what that angle is so we can get the real angle.
53.13.
53.13. Therefore, the real angle measured counterclockwise, because the real angle we are interested in is that one, counterclockwise. So the real angle should be 180 from this, should be 1, 1. Is it 1? Yeah, 180, 1, 2, 6. Again, let me round it off to 9. So, and the magnitude of this line here, again, would be 3 squared plus 4 squared. That is 5. So it should be 5 angle 126.9 degrees. Okay, so I'll remove this. And lastly, so that we finish, we do the same thing. The vector originating at the last pole, the vector originating at the pole, yeah, at -2. At the pole at -2 is given by what? This one now, this pole here. So again, to find this angle, it's 4/1. So the inverse tan, or the inverse tangent of 4. What is that? Should be the one you told me previously. I think it should be 70. Is it 75? You said something, 75 point something.
96.
75.96. So the real angle measured from the real axis should be 180 minus that. So that angle should be let me just round it off. Let's say 104 degrees. So we'll be having, and it's this hypotenuse would be 1 squared plus, that's 5 squared. So that would be root of 25. Am I getting it right? 4 squared, yeah, root of 17. So it would be root 17 angle 104 degrees. Okay. The angles, you can always put them in one decimal point. The angle should be in 1 decimal point. Don't go to 2 decimal points for the angles. So now, because we have all this in polar form, I was actually doing this for you to visualize what we are referring to. So the question again, remember, said find G of S at the point S equals to -3 plus J4. So we terminated all these points of the transfer function to this desired point -3 plus J4. And we found the angles, both magnitude and angles. So it becomes very easy to substitute, so that when to get magnitude over angle, you simply use the illustration, because remember G of S, let me write it here so that I don't keep going back. I think it was S plus 1 over S into S plus, is it 3 or 2? S plus 2. S plus 2. So G of S in terms of the polar form would be, for S plus 1, that was the 0. The 0 was root 20 angle 116.6 degrees over. For the pole at 0, it was 5 angle 126.9 degrees. Notice I write the angles properly. I don't just leave them as decimal points. And then the other one for S plus 2, it was root 17 angle 104 degrees, like that. So like again, like I told you, ladies and gentlemen, here to get the magnitude, you simply have root 20, you must divide by 5 root 17. And to get the angle, you have 116.6 degrees. And because we are subtracting, because we are dividing, we subtract the angles. And the angles down here are 126.9 because they are multiplied here. So we are adding 104, like that, degrees. So then this should give you, anyone who's found this manipulation for the magnitude. So what is the magnitude? Magnitude? Anyone? Okay. So we need to find this is anyone who's got the magnitude?
0.217.
0.217. Thank you very much. And the angle? I have 5 minutes. I need to finish before that.
114.3.
114.3. Thank you very much. Is it 114.3? Because I see this is 116.6 minus, and then I have 126 plus 104. This should be a negative number. Is it minus 114 or
Yes,
114?
It's
minus, eh?
Yeah.
Yes, don't forget that, please. Don't forget that. So it means the answer to the question, find G of my voice is gone. G of S at S equals to minus 3 plus J4 should be equal to 0.217 angle minus 114.3 degrees. The magnitude and the angle. You can actually use your calculator to convert this back to the rectangular form if you want, but this is a sufficient solution. Now, if we didn't have to do this drawing, you'd probably not visualize the way these poles and zeros are in relation to the point that we have. You'd simply just substitute values and solve. Because even here, you could simply punch in your calculator, get the equivalent polar form, get the equivalent polar form, get the equivalent polar form, and you'll still get back here. You still get back here and solve. But I wanted us to visualize how this works because you'll see the importance when we are doing root locus. So thank you very much, ladies and gentlemen. I'll stop here. So from tomorrow, we start our calculations on root locus. So to do that, I will discuss the rules for plotting root locus in the next class. Unless there's a question, I beg to stop here until tomorrow. Again, please, I'm going to send out the, because we're going to have different links that we use for each of the classes. So for the Tuesday classes, I'm going to send out the new link. Please accept my email invitation. Then you can log in automatically as we study in class. So thank you very much. Have a nice day and see you tomorrow. Goodbye.